Hello, my name is Ronan Lee, and for the KSBMB Ignite competition, I will be talking about bacterial cellulose, a detailed analysis, and its prospects. Now, this is a picture. These are some of the pictures that I've created in my research, the bacterial cellulose. And first of all, I'm going to explain what bacterial cellulose is. Bacterial cellulose is the most inexpensive, abundant, and the most durable type of glucose monomers in the world, conventionally synthesized by bacteria. Cellulose is a linear homopolysaccharide made up of beta D glucopyranose linked via beta 1,4 glycosidic linkages. It forms the primary cell wall of green plants, but can also exist in bacteria. On a polymer chain, cellulose can be rich in hydroxyl groups, making it significant in a myriad of industries, from pulp and paper of pharmaceuticals and the production of renewable fuel. However, cellulose alone is challenging to obtain from plants since it's associated with other compounds like lignin, pectin, and hemicellulose. The cellulose used in this experiment is synthesized by bacteria. What caught many researchers' attention are bacterial cellulose's properties. Since bacterial cellulose holds an extremely unique structure, solubly having glucose components, bacterial cellulose manifests an astoundingly high durability, high water retention, as shown in the picture, and high crystallinity. Past research has also proved that bacterial cellulose can make significant advances in the fields of biomedicine, functional devices, water treatment, and nanofillers. The usage of acetic acid bacteria is usually the form of synthesis of bacterial cellulose, and this is exactly what I used to create synthesized bacterial cellulose in my research. There are many types of producers of bacterial cellulose, and still researchers are finding ways to develop the most cost-efficient way to produce bacterial cellulose. Bacterial cellulose is an aerobic gram-negative bacteria that is conventionally fermented in high or normal pH environments. It varies from pH 3 to 7, and bacterial cellulose usually uses monosaccharides as their carbon sources on their energy to grow. The next slide is this is a picture of the intra and intra-hydrogen bonding of bacterial cellulose. To basically explain this picture, it basically shows the bonding of hydrogen bondings among bacterial cellulose, and it shows the chemical properties of bacterial cellulose. So a hydrogel sheet with a large surface area and porosity is formed by, a well-arranged three-dimensional nanofibers that make up bacterial cellulose's fibrous network. As shown in this figure, Acetobacter xylenium forms cellulose 1, a polymer that resembles a ribbon, and cellulose 2, a polymer that is thermodynamically stable. Protofibrils of this glucose chain are extruded throughout the manufacturing process through the cell wall bacteria, where they basically combine to form nanofibrils or ribbons of cellulose. Now, these ribbons use a very porous matrix to create bacterial cellulose's, web-shaped network structure. The cellulose that is produced has a large number of hydroxyl groups on its surface, as shown in the picture, which accounts for its hydrophilicity. It loves water, biodegradability, and ability to alter chemicals. Now, how did we create this? How did I create this during my research? Well, first of all, I'll talk to you about the fermentation process. The fermentation process of bacterial cellulose includes three ways: static, agitated, or stirred conditions. Three-dimensional linked reticular pellicle was seen in the static states. However, irregularly shaped sphere-like cellulose particles were generated in both stirred and agitated conditions. In this condition, in my research, it was actually created in a more like static condition, since our cellulose was very rectangular. And air supply from the medium surface controls the production of cellulose under static conditions, and the yield is somewhat dependent on the concentration of the carbon source. Our carbon source was basically sugar. The carbon source mainly used to create bacterial cellulose is glucose, which is also sugar. To be able to create bacterial cellulose, in the right picture in this slide, you can see the bacterial cellulose with a very circular shape of a culture of bacterial cellulose. And if you see the left picture, it shows a very circular type of material, and this is what's called the SCOBY. Now, the SCOBY stands for the symbiotic culture of bacteria and yeast. A SCOBY is a cellulose mat that bacteria and yeast can live in and latch onto, allowing fermentation. SCOBY is primarily made up of lactic acid bacteria, acetic acid bacteria, and yeast. The SCOBY consists of 37% crystalline structures and 63% nanofibril structure. These structures allow for essential components of the SCOBY, such as biocompatibility, conductivity, and functionalization. In this research, the SCOBY plays the cardinal role of metabolizing sugars to simpler forms, which aids the bacterial cellulose production process. Metabolizing the sugar acts as a primary energy source for the cellulose, and overall, this optimizes the yield of bacterial cellulose. And the SCOBY has, a rubbery texture with a transparent appearance, stained with a little bit of a tan hue. As this research progresses, one observes how the SCOBY, being deprived of nutrients due to bacterial cell production, turns into more like a thin mat with a reddish color. And on the right image, you can see how it turned into like a thin mat, the bacterial cellulose created by the SCOBY. So what is my aim for this research? My first aim is to replace bags, plastic bags. Second aim is water filtration. And the third, most important, is to prevent soil erosion. First aim, biodegradable packaging. Now, the aim of utilizing bacterial cellulose for biodegradable packaging is rooted in the need for sustainable alternatives to conventional plastics. Traditional plastic packaging poses significant environmental challenges due to its non-biodegradable nature, leading to long-term pollution in landfills and oceans. Bacterial cellulose offers a promising solution due to its natural ability to decompose without leaving any harmful residues. Research in this area focuses on optimizing the production of bacterial cellulose to create durable and flexible packaging materials. These materials would not only reduce plastic waste, but also diminish the dependence on fossil fuels, which are currently used in many of plastic productions. By advancing biodegradable packaging, the goal is to create a circular economy where packaging materials can return to the environment without causing any harm, thus promoting a more sustainable, a more eco-friendly lifestyle. Our second aim is water filtration. Bacterial cellulose possesses very unique structures, as shown in the second slide, that make it a quite perfect and excellent candidate for water filtration applications. Its high porosity, first of all, and large surface area enable it to trap a wide range of contaminants, including bacteria, heavy metals, and microplastics. The aim of this research is to develop efficient and cost-effective water filtration systems that leverage these properties to provide clean and safe drinking water, especially in areas where do not have access to clean waters. And our third aim, and most important aim, is soil erosion control. Soil erosion is a significant environmental issue, especially here in Panama where I live, that leads to the loss of fertile topsoil, decreased agricultural productivity, and increased sedimentation in waterways. The aim of using bacterial cellulose in this context is to create solutions that can stabilize soil and prevent erosion. Bacterial cellulose can be processed into mats or films that can be applied to the soil surface. These materials help protect the soil from the impact of wind and water, reducing the risk of erosion. Additionally, they can retain moisture, support the growth of vegetation, and gradually decompose, enriching the soil with organic matter. This research seeks to develop biodegradable erosion control products that are both effective and environmentally friendly. Well, that was it, and thank you for listening to my video. I hope you consider my proposal for my research. Thank you very much.